Rates of change, the basics. Objectives. By the end of this lesson, you should be able to define a quantity, define a rate, define average rate of change and instantaneous rate of change, relate position, velocity, and acceleration, describe horizontal and vertical motion of an object along a straight line, give the conditions for an object speeding up and slowing down, and explain the difference between distance and displacement. We're going to begin our discussion on rates of change by talking about the difference between a quantity and a rate. So a quantity is defined to be an amount of something. So some examples include we can have 10 books, or 13 feet of something, or 2 pounds of something, or 50 miles, as opposed to a rate, which is a ratio of two different quantities. So some examples of a rate, so we're looking for a ratio, so ratio we think fraction, so two different quantities, so 10 books over 1 month. So this ratio would read 10 books in 1 month, or 13 feet every 2 seconds, or maybe you lose 2 pounds in 1 week, or go 50 miles in 1 hour. So to have a rate, I need a ratio of two different quantities so that the units don't cancel out here. So books and month are different, feet and second are different. So I can read 10 books in 1 month, or travel 13 feet in 2 seconds. I can lose 2 pounds every 1 week, or travel 50 miles in 1 hour. These would be examples of some typical rates that we're going to deal with in this section. Alright, so now let's think about the graphical interpretation of a rate. So let's remember that slope is equivalent to rise over run. So graphically, it turns out that a slope is equivalent to a rate if the quantities on the axes are different. So remember that a rate is a ratio of two different quantities. So as long as the units on the horizontal and the vertical axis are different, then it turns out that our slope is going to be equivalent to a rate. So remember that a slope, as is written, is rise over run. So let's go ahead and think about one of the previous examples of a rate that we just took a look at. So we can lose maybe on average 2 pounds in 1 week. So this was an example of a rate. And let's think about on which axes each unit goes. So rise, we think up and down, so that would correspond to the y-axis. And run, we think of as left or right, and that would correspond to the x-axis. So when I think about how to label my units here, my unit of pounds is going to go on the y-axis, and then my unit of weeks is going to have to go along the x-axis, or the horizontal axis. So I don't really want to stick with x's and y's because we are going to change that up a little bit. So on my horizontal axis, I'm going to go ahead and label the unit as weeks. And so now, after 1 week has passed, I would have then lost 2 pounds. So I'd go over to 1 week on the horizontal axis and go up to 2 pounds on the vertical axis and label that coordinate point. And from that coordinate point, I can figure out how many pounds I would have lost after 2 weeks. So after another week has passed, I would have lost another 2 pounds, so I would be up to 4 pounds total. So I'll go ahead and mark that point on the graph. And after 1 more week has passed, so now I'm at 3 weeks, I would have lost another 2 pounds. So we can see that between the first week and the second week, if I were to connect the dots there, that my average weight loss between week 1 and week 2 would be 2 pounds, which translates to rise over run. So let's do that in a different color. So I would go up 2 units, but my units are pounds, so this is 2 pounds, and then I would run over 1 week. So graphically, my rate is just the slope. So in this case, this represents an average rate of change. On average, I lose 2 pounds in 1 week. And we'll get into the difference between an average rate of change and an instantaneous rate of change. Alright, to get into the difference between an average and an instantaneous rate of change, let's look at this particular example. So we're going to consider a car that's traveling along a road for a 4-hour time period. At different moments in time, the distance traveled by the car was recorded as provided in the table below. So here I have this table. That's all I would have been given. So t is in hours and the distance d is in miles. So at time 0, I haven't gone anywhere, so I've traveled a total of 0 miles. At 0.5 hours, or at 30 minutes, right, because our time is in hours, so at a half an hour or 30 minutes, I have then traveled a total of 25 miles. After 1 hour has passed, I've traveled 40 miles. After 2 hours, 85 miles. 2.5 hours, 100 miles. And then we jump all the way to the end of our trip. We've traveled 4 hours and we've gone a total of 180 miles. So let's assume we were given just this table of information. So each of these pieces of information correspond to coordinate points. So at time 0, I've traveled 0 miles. So if I go ahead and think about that on a graph, translating to coordinate points, well, along my vertical axis, I'm going to go ahead and have miles as my units, and along my horizontal axis, I'm going to go ahead and have hours as my units. So at time 0, I've traveled 0 miles, so I'm right here at the origin. But after a half an hour has passed, after 0.5 hours, so right here at 0.5, I have traveled a total of 25 miles. So that corresponds to this coordinate point here. And then after 1 hour, I've traveled 40 miles, and so on and so forth. So each of these blue points here correspond to the different coordinate points from the table of data. So first things first, I cannot connect the dots. So I don't have enough information about every other moment in time on the trip. I only have snapshots of information. So how far I had traveled at these different times. So at 0, at a half an hour, 1 hour, 2 hours, 2.5, and 4 hours. But I have no idea how far I had traveled in between these amounts of time. So here's the type of question we might be asked that corresponds to this table of information. On average, how fast was the car traveling during the first 30 minutes of the trip? So let's try to bring in the quantities we're trying to talk about here. So we have hours and we have miles, so we have time and we have distance. So hopefully you're thinking of the familiar equation, distance equals rate times time. And so what we're solving for here, we're solving for a rate. How fast was the car traveling during the first 30 minutes of the trip? So if I want to isolate this r, this rate, well, I can go ahead and divide by t. So let's write that out in words now. Distance over time is equal to a rate. So I'm going to go ahead and put a little asterisk here because this isn't entirely correct, and we'll get to that in a second. But in general, this is just bringing in some knowledge that we should already have. Distance equals rate times time. We have units of a time, we have hours, we have units of a distance in miles. And so dividing by distance, we can get out a rate, which is how fast something's going, is a rate. So how fast was the car traveling during the first 30 minutes of the trip? So we have to know the distance traveled. Well, during the first 30 minutes, so remember that 0.5, this corresponds to 30 minutes. So over the first 30 minutes, I started out at 0. I ended up traveling 25 miles. So my distance that I've traveled is 25 miles. And then how long that took me was a half an hour. So I'll go ahead and put 0.5 hours. So here, 25 miles over 0.5 hours, well, that's 25 over a half miles in an hour. So 25 divided by half is 50, and hopefully you're thinking, well, miles in an hour, that's miles per hour. So on average, I was traveling 50 miles per hour over the first 30 minutes of my trip. So why do I have to say on average? Well, at time 0, I knew I was going 0 miles per hour because I hadn't gone anywhere. I hadn't started moving at all. So how do I know that between 0 and 0.5 hours that I didn't end up looking maybe something like this? So there's no way at every single moment in time I can say I was going 50 miles per hour between the first 30 minutes of the trip. So I have to increase my speed incrementally. So I can't just be going 0 miles an hour and then as soon as I start driving, all of a sudden I'm going 50 miles an hour. I have to gradually increase to that amount. So on average, I was traveling 50 miles an hour if I traveled a total of 25 miles in 30 minutes, but there's no way I was going 50 miles an hour at every single time between 0 and 30. So that's the difference between the average and the instantaneous. So at a particular moment in time, let me get a different color. At a particular moment in time, if I calculated the slope of that tangent line at a particular moment, that's how fast I'm going at any particular time. That's my instantaneous rate of change. At that one moment, the slope of that tangent line represents how fast I'm going. But between 0 and 30, just computing how far I went over how long it took me is going to give me, on average, how fast I was going at any particular moment. It's going to give me an approximation. So what I'm essentially finding in an average rate of change is the slope between these 2 points. So if I find a slope between 2 points, I found the slope of a secant line. But if I want to know exactly how fast I was going at 0.25 hours, so after 15 minutes of traveling, well then I would need to find the slope of a tangent line, which is a derivative. So let's sort of keep going and let's answer the second question. On average, how fast did the car travel during the entire trip? So the entire trip being over the course of 4 hours. So we use this same formula here, and I'll go ahead and do that work up here. So if I want the rate, it's going to be the distance traveled. So at 4 hours, I've traveled 180 miles, and then over the course of 4 hours. So if we go ahead and simplify this, on average, so I should include units. So 180 miles over 4 hours, 180 divided by 4 is going to be 45 miles per hour. So between the first 30 minutes, on average, I was traveling a little faster at 50 miles per hour, but over the course of the whole trip, so from time 0 all the way up to that last point, the slope of this line is 45. So on average, on the whole trip, I was traveling 45 miles per hour. So can we determine exactly how fast the car was traveling at a particular moment or instant in time with the information provided? The answer there is no, because I can't fill in the dots. I don't know exactly what's happening in between each of those times. So in between each of these moments in time I've collected information, I might be doing something weird like that. So in order to find exactly how fast I was going at a particular moment in time, we mentioned we would need the slope of the tangent line. Well, to have the slope of the tangent line, I would actually need the exact function. So whatever this crazy wavy line ends up being in terms of a function, I would need that function so I could take its derivative and then substitute in that moment of time to find the exact speed at that moment, or how fast the car was going. So here I can only find an average rate of change, an average speed, if I only have pieces of information. So to find an instantaneous speed, I would need the original function. Alright, let's formally summarize the results of an average rate of change. So the average rate of change, often abbreviated ROC, is defined to be the displacement over time elapsed. So displacement is different than distance, and we will discuss the difference between the two in a moment. We can also think about the average rate of change over the time interval from t0 to t1 as the change in the position over the change in time. So we think about that mathematically as delta S, where S is the position, over delta T, so the change in the position over the change in time, which translates to S of T1 minus S of T0, so the position at time 1 minus the position at time 0, over time 1 minus time 0, so that difference in the time that has passed. Or even more generally, we could think about the average rate of change over x sub 0 and x sub 1. So in general, we want the change in y, or the change in the vertical axis, over the change in the horizontal axis, so delta y over delta x, which would be f of x1 minus f of x0 over x1 minus x0. So hopefully you could recognize this as the difference quotient, or the slope between 2 points. So graphically, as we've mentioned, average rate of change is the slope of the secant line, so a secant line between 2 points. So note that you might be asked to find the average rate of change or to approximate the instantaneous rate of change. So to determine whether you're finding average rate of change, they might outright tell you to find average rate of change. Or another way to ask you would be to approximate the instantaneous rate of change. Alright, now let's talk about the difference between distance and displacement. Distance is a quantity that measures the length of the entire path that's traveled, as opposed to displacement is the net change in position, or the straight line distance between the initial point and the final point, or the initial position and the final position. So let's imagine that this is a path that we're about to take. So I'm going to go ahead and say this is the starting point and this is the ending point. And we'll go ahead and say that this vertical distance here is, let's go ahead and say 10 feet. This one's 10 feet, 10 feet, and then this little distance here is 5 feet. So if I wanted to ask what is the total distance traveled, that's the length of the entire path traveled. So the distance would be 10 plus 10 plus 10 plus 5. So 10 plus 10 plus 10 plus 5. So my distance traveled is a total of 35 feet. As opposed to displacement is the net change in position, or the straight line distance between the initial position and the final position. So my displacement, well, the straight line distance between the starting point and the ending point, this straight line distance is only 5 feet. So the displacement is only 5 feet. So that's the subtle difference between distance and displacement. So in general, the distance is always greater than or equal to the displacement of an object. Alright, so now to formalize instantaneous rate of change, or really just the derivative. So instantaneous rate of change is the limit as delta t, or the change in time, approaches 0 of the difference quotient delta s over delta t, or the limit as t1 approaches t0 of s of t1 minus s of t0 over t1 minus t0. And this is exactly the limit of a difference quotient, so this is s prime of t0. This is the derivative of the position at a particular time. So in other words, instantaneous rate of change is equivalent to the derivative at a particular moment in time. Or we can generalize it with y's and x's, so the limit of delta x, as delta x approaches 0, of delta y over delta x, which translates to this difference quotient, f prime of x0. So when asked to find instantaneous rate of change, it's equivalent to asking to find the derivative. And the derivative, we said, was the limit of a difference quotient, the slope of a tangent line, and finally, the instantaneous rate of change. So graphically, instantaneous rate of change is the slope of the tangent line at a particular time. So now we're really connecting those three different definitions of the derivative at this time. So note, you might be asked to find the instantaneous rate of change or rate of change only. So a lot of times they drop the word instantaneous. So if you're asked to find the rate of change, you are to assume it's the instantaneous rate of change. So the bottom line is, instantaneous rate of change is the derivative at a particular moment in time. Alright, now let's explore the relationship between position, velocity, and acceleration. So suppose we're given a position function and we're going to call it s of t. To find the velocity function, v of t, we take the derivative of the position function, so s prime of t. So in other words, the derivative of position is equal to velocity. Now, if we're interested in the acceleration function a of t, then we have to take the derivative of velocity, which is equivalent to taking the second derivative of the position function. So the relationship is the derivative of the position function is the velocity function. The derivative of the velocity function, or the second derivative of position, gets me to acceleration. So this is a very important relationship to understand. And some other questions that might be asked involving velocity and acceleration are for average velocity or average acceleration. So to find average velocity on the time interval from t0 to t1, average velocity is the change in position, so the previous function, over the change in time.
So average velocity graphically is the slope of the secant line on the position graph. And if I want average acceleration over a time interval, well, average acceleration is the change in the velocity over the change in time. So graphically, average acceleration is the slope of the secant line on the velocity graph. So again, the average velocity, I need the change in position over the change in time. For average acceleration, I need the change in velocity over the change in time.
The next definition is the definition of speed. So speed is considered to be the absolute value of velocity. So speed, notationally, the absolute value of velocity, or the absolute value of v of t. So in other words, speed is always a positive quantity. So whereas velocity takes into account direction, so if velocity is positive, I'm either moving to the right or up. If velocity is negative, I'm moving to the left or down. Speed is just how fast are we going. It doesn't matter what direction we're going. So speed is always a positive quantity. Alright, the next few pieces of information are going to be facts that you need to know about rectilinear motion, which is just movement of an object along a straight line. So, because we can have two different types of straight lines, we can have horizontal and vertical straight lines, it's important we talk about both. So if we have horizontal linear motion, if velocity is positive, then the object is moving right towards positive infinity. So think about an object moving along the x-axis. If we find out that velocity is positive, then the object will be moving right towards positive infinity. But if we find out velocity is negative, then the object is moving left, so on the x-axis towards negative infinity. If on the other hand we have vertical linear motion, and we're told velocity is positive, then the object must be moving up or rising. So we can think about moving up along the y-axis. And if velocity is negative, then the object is moving downward or falling. So we're thinking moving down along the y-axis. Alright, so now we're going to talk about the speed of an object to be increasing versus the speed of an object decreasing. So we're still thinking about an object moving along a horizontal or vertical line. Now, at a particular moment in time, an object has speed increasing, or is speeding up, if both velocity and acceleration have the same sign at that time. So if at a particular moment in time, both velocity and acceleration are either both positive or both negative, then an object's speed is increasing, or that object is speeding up. As opposed to an object has a speed that is decreasing or is slowing down if velocity and acceleration have opposite signs. So one of them is positive and the other one is negative. So to think about this, I always talk about if you're driving in a car and you're stepping on the gas in a forward motion. So if velocity is positive, meaning that you're moving forward, and you accelerate, so you step on the gas, then velocity and acceleration have the same sign, so you're going in a forward motion and you step on the gas to accelerate, then you're going to be speeding up in the car. Well, similarly, although it would be really dangerous, you could be in reverse, so your velocity would be negative, you would be going backward, but you could still be accelerating in a negative direction, so you can step on the gas. So if velocity and acceleration both have negative signs, meaning that you're going backwards, you're still speeding up, just in reverse. Dangerous, but possible. So that would be an example of speeding up in terms of velocity and acceleration having the same sign. But if on the other hand, when are you slowing down? Well, if you're on the freeway and you're going in a forward motion, so your velocity is positive, but then you start to hit on the brake. So hitting on the brake would be decelerating. So that would mean your acceleration has a negative sign, but your velocity still has a positive sign because you're moving forward in a positive direction. But in that case, you would be slowing down. So if you're driving in a forward motion because velocity is positive, but you're stepping on your brake, so you're decelerating, so acceleration is negative, that would be an example of slowing down. Alright, so now we're going to look at an example of linear motion. So consider the following problem. A student walks away from the origin to a displacement of 8 meters in a total of 10 seconds. So let's just first think about there being an origin,
and this person starting at the origin. And the person's walking away from the origin to a displacement of 8 meters in a total of 10 seconds. So let's say they're moving to the right and they travel to a displacement of 8 meters. And let's say this took a total of 10 seconds. So we're just trying to track each of the person's movements. So they started out right here, and this was considered to be at time 0. And after 10 seconds, now the person is over here, and let's go ahead and call that time 1. Now the student stands still for a total of 10 seconds. So now they're not going anywhere, they're just standing right here for a total of 10 seconds. Then the student walks 4 meters toward the origin in 4 seconds. So let's do that in a different color. So now they're walking back this way over a total of 4 seconds is how long it takes them to travel 4 meters toward the origin. So they're going to shrink a little bit. And they're going to go 4 seconds, and if they go 4 meters back toward the origin, that leaves them at 4 meters. And then the student's going to stand still again for 6 seconds. And then the student's going to walk away from the origin again to a displacement of 14 meters in 5 seconds. So now a displacement, so that would be the straight line distance from the origin to that location. So a displacement of 14 meters. So they're going to end up over here at 14 meters in 5 seconds. So that means they're going to turn around and go back all the way over here to 14 meters in a total of 5 seconds is what it will have taken to get over here to 14 meters. So that's what's happening along the straight line. So now let's think about that in terms of a graph. Alright, so here was our linear motion along a straight line, just thinking about what's happening, but ultimately we want to put this on an XY plane, or at least a horizontal and vertical axis plane. So here's our horizontal axis that's going to have units of time in seconds, and our vertical axis is going to have a units for displacement, which is in meters. So this would be considered our position graph. So this is our position graph or our position function. So let's see how each of these movements translated on a graph. So we had our student that started at the origin, so at a displacement of 0. He hasn't gone anywhere, so he starts out right here. And then he walked away from the origin to a displacement of 8 meters in 10 seconds. So on our horizontal linear graph up here, we just started this man off at 0, and then he said 10 seconds later he ended up over here at 8 meters. Well, on this position function, over the course of 10 seconds, so these are marked by tick marks of 2, so over the course of 10 seconds, he ended up reaching a displacement of 8 meters. So this is where he ended up. So this is the first motion. Well, then the student stands still for 10 seconds. So on our just linear graph here, I'm just trying to understand his path, we really couldn't represent standing still for 10 seconds. But on this position function, we can. So between 10 seconds and over here at 20 seconds, we can say between 10 and 20, he was standing still, so his displacement was nothing. He was at 8 meters, and he just stays at 8 meters, a constant 8 meters for a total of 10 seconds. So that can now be represented on this XY graph, or this time meters graph. Well, then the student walks 4 meters toward the origin in a total of 4 seconds. So we pick back up at 20 seconds when he stopped just standing there, and he's moving toward the origin. So the origin being the horizontal axis here. So he's moving back toward the origin, a total of 4 meters in 4 seconds. So between 20 and 24 seconds, he travels from 8 meters all the way down to 4 meters. And then the student stands still again for 6 seconds. So between 24 and 30 seconds, this student is standing still. So he's not going anywhere. It's just a constant horizontal line now. And then the student walks away from the origin to a displacement of 14 meters in 5 seconds. So he was at 4 meters, and then between 30 and 35, this should be 35 seconds, between 30 and 35 seconds, he goes from being at 4 meters to 14 meters. So on this graph, what we're thinking about is not only thinking about the time and the displacement, but we're thinking about the slopes. So the slopes tell us the rate, how fast he was going on average, right? Because we really only have little snippets of information here. So between 0 and 10 seconds, if his displacement was 8, so he went up 8 and then over 10. So up 8 over 10 is going to be 4 over 5 meters per second. So on average, he was traveling 4 over 5 meters per second. And then between 10 and 20, how fast was he going? Well, my rise over run, my rise is 0 over run, so I'm going to have 0 over a number, which is 0. So that means he wasn't moving at all, so his rate of change is 0, which the slope of the tangent line, the slope of this line is 0. So here, this one is a negative slope, but what does it mean to have a negative slope or a negative derivative of position? Just means that my object is moving back towards the origin, right? Or back towards the left, towards negative infinity. So let's look back up here. When I was going 4 seconds and 4 meters, if I was going to the left, that was towards negative infinity. And that's because right here I'd have negative slope. So I went down 4 in 4 seconds, so my slope right here is -1. And then right here my slope is 0. And then at the end, my slope is pretty steep and positive. So I'm moving to the right because my slope is positive, and I'm moving a little bit faster than I was over here because my slope here is steeper. So my slope here is a rise 10, right? So my units here is I'm rising 10, and I'm going in a total of 5 seconds. So rise over run, 10 over 5 is going to be 2 meters per second. Is going to be the slope right here. So 2 meters per second. As opposed to over here, this was the rise of 8 and the run of 10, so this was 4 over 5 meters per second. So I'm going a lot faster over here than I was over here. And I can tell I'm not going any rate of change on these intervals, this 1 over 2 and 4. And then I'm going negative rate of change, but that just means that I'm going toward negative infinity. So this one was -1. Alright, the last thing we're going to take a look at with this problem is the difference between the position graph and the velocity graph. So last time we analyzed that position graph, that position function that's shown right here, and we did take a look at each of those slopes. So we said that this slope was 4 over 5, and this slope is 0. This slope here was -1, this slope was 0, and this slope was 2. So slopes represent the derivative. The derivative of position is velocity. So in other words, I could go ahead and graph my velocity function now with my units of time along the horizontal axis, but this time my vertical axis is going to be in units of meters per second. So this is a velocity function, so now my units are going to be in meters per second, a rate. So between 0 and 10 seconds, my velocity was a constant 4 over 5 because this was going to be an average graph here. So the average velocity here is going to be 4 over 5. And then from 10 to 20, my rate of change was 0. My velocity was 0, so 0 is just going to be on the horizontal axis. Here, when I was going away from the origin towards negative infinity, my slope of -1 would translate to a horizontal constant slope of -1 from 20 to 24. Again, when I'm standing still, my velocity is 0. And then between 30 and 35, my velocity is 2 every time. So I can also graph a velocity function. And as we continue to move forward, we are going to analyze position graphs, velocity graphs, and even acceleration graphs. Alright, so what I wanted to do now is comprise a list that's the basics in rates of change. So sometimes students don't have an intuition for a lot of these concepts, and if you've seen physics before, then that's going to give you a little bit of a foundation for this, but otherwise it's just important to know what each of these keywords means. So if you see the word initial or initially, that translates to time being equal to 0. So if you think about initially, it means the start of something. So that would mean that we're going to let time, t, equal 0. If a problem says at the origin, Well, that means that the position has to equal 0. So at the origin, meaning at the starting location, so the location translates to position. So at the origin means we're going to have to set the position function equal to 0. When a problem says that an object is at rest, that means that the velocity has to equal 0, or the speed has to equal 0. So when an object is at rest, when it's not moving, then that means its velocity is equal to 0. So now if a problem asks you for the maximum height of a ball being thrown into the air, so the maximum height of a ball being thrown into the air, so we can think about that. If I throw a ball into the air, when it reaches its maximum height before it turns and goes to the ground, at its very maximum height, it's going to stop. And if it's going to stop, that means the ball is going to be at rest. So when an object was at rest, we set the velocity equal to 0. So to find the maximum height of a ball being thrown into the air, well, that occurs when the velocity equals 0. So once we find that time, when the velocity equals 0, then we take that time and we plug it back into the position function, because the problem is asking us for the maximum height of the ball. So if a problem is asking us for a height, we don't want to give an answer that's a time. But to find the maximum height, we're going to have to find the time when the maximum height is achieved, and that time is going to occur when velocity equals 0. Another key phrase is if an object is dropped. So if an object is dropped, that tells us that the initial velocity, so the starting velocity, must have been 0. Because if you drop something and you're holding it in your hand, it's not moving to begin with. So initially, at the start, the velocity is 0. When an object is in vertical motion and it hits the ground, so when you throw a ball up into the air and it hits the ground, its height is 0. So when an object in vertical motion hits the ground, its height is 0. Now a lot of students want to say its velocity is 0, and that's not true. So when an object, the moment an object hits the ground, its velocity can't be 0. Because otherwise, if you threw an egg up in the air, when it hits the ground, if its velocity is 0, the egg wouldn't break. But we know that it does, because it has a velocity at the moment it hits the ground. Now, a second after an object hits the ground, then yes, its velocity is 0 because it's not going anywhere anymore. But in general, if we're trying to find when an object in vertical motion hits the ground, we need to know that time where it happens. And that time where it happens is when its height is 0, because its height off the ground will be nothing once it hits the ground. If asked when, or at what time, or how long, our answer needs to be a time. Now this may seem obvious, but over and over again, once we start developing more and more topics, a lot of students get confused on what the problem is asking. So we need to be able to find these key phrases or identifiers. So when asked for when, we know their answer needs to be a time, and that's why we always include units in our answer. Now if asked to find a speed, a velocity, how fast, what is the rate, or for a rate of change, well, then our answer needs to be a rate. So key phrases that you're being given a rate of change are when words like per, for, and in are used. So some examples of that are if you're told someone reads 3 pages in 10 minutes, you've been given a rate. 3 pages over 10 minutes, there's my ratio. Or 5 miles per hour, you've been given a rate. Again, there's that keyword per. Or something is selling for 10 bananas for $3. So that word for indicates that you're given a rate. So remember what a rate is. It's a ratio of 2 different quantities. So my quantities here are bananas and dollars, and miles and hours, and pages and minutes. So these are all really basic facts. They're great things to go ahead and put on a note card to try to memorize and identify all of these different key phrases that can and will appear in problems. Alright, the next thing I want to talk about is units involved in rates of change. So distance is in linear units. So examples of distances are feet, inches, miles. Area, on the other hand, is in square units. So examples of area are feet squared, inches squared, miles squared. And then volume is in cubic units. So feet cubed, inches cubed, and miles cubed. And all of these, again, you might think are pretty basic, but where students start to get confused is when we talk about position, velocity, and acceleration, because position functions like x of t or s of t, so those are the typical notations for position functions, have units that are a quantity. So position functions, and I put that in quotes because they don't really always have to be positions as in locations. What we really just mean is that these types of functions have units that are a quantity. And remember, a quantity is just an amount of something, of anything. So typical examples might include distance, area, and volume. Those are all quantities. But they can also be in units of money, people, rocks, desks, or really absolutely anything, because position functions have units that are a quantity, and a quantity is an amount of something, of anything. Now, velocity functions, and I put that in quotes because really just the derivative of any position function or the derivative of a quantity function must have units that are a quantity over a time. So that's because these express rates. So remember that the derivative of position is velocity. A velocity is a rate of change. So a rate, as we've said at the very beginning, is a ratio of two different quantities. So these derivatives of position functions need to look like feet over second, so a quantity over a time, or people per year, or dollars per hour, or rocks per minute. Or right now it looks like maybe these examples need to be a linear unit, so feet. But examples could be feet squared over seconds, because the unit on the top has to be a quantity, and a quantity, if we want it to, could be an area, so feet squared per second, or even feet cubed per second, so a volume over a second. So velocity functions need to be some quantity over a time. Now, acceleration functions, or the derivative of a velocity function, is a rate of change of a rate of change. Now, these must have units of a quantity over a time squared. So what that means is examples might include feet per second squared, or miles per hour squared. So units of the derivative of a velocity function, or a rate of change of a rate of change, so the second derivative of a position function, these have to have units where the time unit is squared. So it's important to understand the difference between the time unit being squared and the quantity unit being squared. So I know that I have an acceleration function when my time unit that's on the bottom of this rate is what is squared. So this one up here, when I went ahead and said feet squared per second would be a unit of a velocity. So feet squared is a quantity. So this is an area over seconds. This is an example of a velocity, but a lot of people get it confused with feet per second squared, which is an acceleration. So acceleration has to have my unit of time that's squared, as opposed to my velocity functions just need a unit of time, not squared, but the unit of the quantity can be squared, can be cubed, that doesn't matter. So the concept of the units in rates of change really saves you a lot of time in trying to understand what a problem is asking for. So if you really understand units, that can take you really far in these types of problems. All right, let's look at this example with multiple parts. Let x of t equal t cubed minus 3/2 t squared minus 18t plus 30. And that's going to represent the position of a particle that's going to travel along the x-axis, where t is given in seconds and x of t, the position, is given in inches. For part A, find the position of the particle at t equals 1 second. So I'm interested in finding the position, and I'm given the position function. So if I want the position at time t equals 1 second, and t is in seconds, I need only substitute 1 into t into this equation, and that will give me my position in inches. So for part A, I'm interested in x of 1. So I'm going to plug in 1 everywhere there's a t. So 1 cubed minus 3/2 times 1 squared minus 18 times 1 plus 30. And I'm going to skip the arithmetic here and tell you that this is 11.5 inches. Because remember that x of t, so x at any time, is given in inches. So now for part B, I'm asked to find the velocity at time t. So I'm given the position function s of t. To find velocity in general, right, this is at just some time t, I need to take the derivative of position. So v of t is equal to x prime of t, so the generic derivative of position. And this is nice because we can just apply the power rule. So x prime of t is 3t squared minus 3t, when I bring that 2 to the front, it'll cancel with the 2 on the bottom, minus 18. So there's my velocity function, and I should include units. So my velocity is a rate. So the rate is going to be in inches per second. So this quantity over the time. All right, so part C, scroll down a little. Part C, what is the velocity after 2 seconds? So now I have this velocity function in terms of t. So for part C, what's the velocity after 2 seconds? All I'm being asked to do here is substitute the 2 into my velocity function. So 3 times 2 squared minus 3 times 2 minus 18. And skipping the arithmetic again, I'm going to get negative 12. And my units are velocity, so inches per second. So now let's move on to part D. When is the particle at rest? So in general, it's when is the velocity, v of t, equal to 0 when a particle is at rest. So v of t is this function here. So 3t squared minus 3t minus 18 equals 0. So to set this equal to 0, I'm going to have to factor it. So let me go ahead and pull the 3 out that's common in everything. So 3 times t squared minus t minus 18 equals 0. So this part right here will factor to 3 times t minus 3, t plus 2 equal to 0. So now I set each part with t's equal to 0. So sometimes students want to set 3 equal to 0, but that wouldn't make sense, right? Because 3 can never be 0. So I'm going to set t minus 3 equal to 0. So t equals 3. And then t plus 2 equal to 0. So t equals negative 2. Now let's keep in mind the units here are in seconds, so one of these should very obviously not make sense, which is t equals negative 2, because I can't have negative time. So this is not an answer, so I wouldn't take the absolute value of it, I would just ignore it entirely. I cannot have negative time. So in answer to when is the particle at rest, the particle is at rest at t equals 3 seconds. So at 3 seconds, the particle is at rest. Alright, so now let's move on to part E, and we needed some more space for that. So when is the particle moving in the positive direction? So for part E, an object is moving in the positive direction when v of t, the velocity, is greater than 0. So the velocity function right here, which was 3 times t squared minus 3t minus 18, I want to know when that function is greater than 0. So one of the easiest ways to solve this problem is to be able to graph it. So we already did a lot of the work when we factored it to be 3 times t minus 3 times t plus 2 is greater than 0. So what we just did was we found the x-intercepts. So if I were to graph this function, I know that one of the x-intercepts is negative 2 and the other is 3. And I know that the y-intercept is negative 18. And because this is a quadratic, it's going to look like a open upwards parabola. Because my leading coefficient is 3, it's positive. So it's going to look something like this. Now, it's very important to know that although this is the generic derivative function, the velocity, I'm only considering portions of this graph to the right of 0, because remember that the horizontal axis is time in seconds, and I can't have negative time, so I don't care about what's happening at all over here to the left. So I'm only interested in the portion of the graph over here on the right side. And what we're asking here is when is velocity greater than 0? So this is my velocity graph. This is v of t. I just graphed v of t. So when is this parabola greater than 0 is like asking when is this graph above the x-axis. So this graph, just to use one more color, is above the x-axis whenever x values are greater than 3. So this x coordinate was 3. So from 3 to infinity, open at 3, because I want to know when this is strictly greater than 0, from 3 to infinity, this velocity graph is greater than 0. So when is the particle moving in the positive direction? Well, first we have to know that that means when velocity is positive, when velocity is greater than 0. The velocity function is this quadratic. And how do you set a quadratic greater than 0? So the easiest way to do this would be to graph it. And then we're understanding conceptually that time has to be positive, so I only care about what's happening to the right of the vertical axis, so to the right of 0. And then this is understanding how to read a graph and when a graph is positive or above the x-axis. Alright, now let's work on part F. Find the acceleration at time t. So acceleration is the derivative of velocity, so a of t is v prime of t. So v prime of t, well, let's go back. Here's v of t right here, 3t squared minus 3t minus 18. So the derivative of this using the power rule is just 6t minus 3. And now my units of acceleration are going to have to be inches per second squared. So my units of acceleration have a time that's squared. So now for part G, when is acceleration positive? So when is a of t greater than 0? So a of t is 6t minus 3. So when is this greater than 0? Because this is a linear function, this one's easier to solve than one as a quadratic greater than 0. So 6t minus 3, we can solve this analytically by adding the 3 to the other side, dividing by 6. So this is when t is greater than 1/2. So an interval notation from 1/2 to infinity. So acceleration is positive for time values from 1/2 to infinity. So this was a time interval as well. So this is t time in 3 to infinity, and this is time in 3 to infinity or 1/2 to infinity as well. So for part H, when is the speed of the particle increasing or decreasing when t equals 2 seconds? Sorry, this when shouldn't be here. The question is just, is the speed of the particle increasing or decreasing when t equals 2 seconds? So hint, when v of t and a of t have the same sign. So is the speed of the particle increasing or decreasing? We need to see what's going on at v of 2 and at a of 2. If they both have the same sign, then the speed is increasing. If they have opposite signs, the speed is decreasing. So v of 2 we actually already found in part C. So v of 2 is negative 12 inches per second. And a of 2, so we could, if we want, just go ahead and plug 2 into a of t. So that would give me 6 times 2 minus 3. So that's going to give me 12 minus 3, which is 9. So this is positive, so 9 inches per second squared. So velocity is negative, acceleration is positive 9, so the speed is decreasing. But in fact, we actually didn't even have to plug in 2, because in part G, we found that whenever time is between 1/2 and infinity, the acceleration is positive. So 2 is in this interval, so we knew that a of 2 was going to be positive. But substituting in 2 was okay, and we already had v of 2 from part C. So since velocity is negative and acceleration is positive, speed is decreasing. And we would want to write that since a of 2 is greater than 0, which means positive, and because v of 2 is less than 0. So we were at the point where we need to justify our work, so this right here is the justification. Alright, so we now have to work on part I, and part I is going to take a little bit of thinking about. Find the total distance traveled by the particle during the first 3 seconds. So first I want to go back and think about that man that was walking on a horizontal line for a second. So he started out at the origin or at an initial location, and then after 10 seconds had passed, he traveled 8 meters. So 8 meters in a total of 10 seconds, and this is where he ended up. And then he stopped. And then some time passed, and then he turned back and went 4 meters back toward where he was in the first place, and that took a total of 4 seconds. So if I wanted to know, let's just say that was the end of the path, so he ended up back right here. So if I wanted to know the total distance traveled, well, I would have to know how far he went from 0 in the first 10 seconds, so that was a total of 8 meters, and then he stopped, and then he went backwards, and so I'd have to know how far he traveled from when he stopped to that next 4 second, over that next 4 seconds for a total of 4 meters. So I would have to add 8 meters and 4 meters together. But the key is where he stopped. So I would need the distance from, let's call this time 0 to time 1. So I would need that distance from time 0 to time 1. So that would be s of t1 minus s of t0. So I need that distance between those original times, but then I would also need to add the distance from traveled between time 1 and time 2. So the distance between time 1 and time 2 is s of t2 minus s of t1. Now we want our distance to always be positive, so what we're going to do is we're going to take the absolute value of both of those quantities, and then we add the two distances together. So the distance between time 0 and time 1, that was 10 seconds in that example, and then or not 10 seconds, I'm sorry, 8 meters. And the distance between the time 2 and time 1, the distance traveled was 4 meters. So this would have been a total of 12 meters. So that's just a modification to that first example, but the key is we needed to know where the man stopped and the two times that we would have to find the distance between. So if I want to know the total distance traveled by the particle during the first 3 seconds, I need to ask myself whether or not this particle stopped during the first 3 seconds. Because if it started at an origin location and then moved to the right and then stopped sometime between 0 and 3 seconds and went back, I would need to add up more than one distance. So we actually answered the question of when was the particle stopped in part D and when is the particle at rest. So it turned out that the particle was at rest at 3 seconds. So that was the first time the particle stopped, was at 3 seconds. So in order to calculate the distance, what I would need to do is just find the position at 3 seconds, so what's s of 3, and subtract the position at time 0. So where I ended up after 3 seconds minus where I started at time 0, and take the absolute value of those two locations, those two positions, and that will tell me how far I traveled. But if I had stopped somewhere between 0 and 3 seconds, then I would have to break it up into more than one interval. So I would have to break it up into different positions because there would be different amounts traveled over different time frames. So I would go back and think about that example of the man walking to think about the total distance traveled. We would have had to add his forward direction distance to how far he went in reverse, and then he ended up actually going back forward again. So we would have had to add up a total of 3 quantities to figure out the total distance traveled for that original man walking in a horizontal line. So for this one, because the particle actually just stopped at 3 seconds, all I need to do is find s of 3, the position at 3, minus s of 0. So in other words, I need to plug 3 into the original function. So sorry, these should have been x's. So x or s is typically used for position. So x of 3, so I need to do 3 cubed minus 3 halves 3 squared minus 18 times 3 plus 30. And that whole quantity minus substituting in 0. But that's kind of nice. If you plug in zeros everywhere for the t's, it's just really going to be minus 30. So this quantity is the absolute value of negative 40.5, which is just positive 40.5. So the total distance traveled is 40.5 inches during the first 3 seconds.